Thank you, Sue, and your team for making this lecture series possible. And thank you all for coming out on an evening where it probably was very easy to decide to stay at home. So I appreciate everybody. And I do have one snowplow slide embedded in the talk in honor of all the people who are dealing with snow. So let me just close this out. And I have a variety of videos that I'll go back and forth between. I just want to put up the title slide before I jump to the videos, and then we're ready to go. So, as Bob said, my name is Rich Collins. I've been with the Geophysical Institute. The talk I put together this evening, I also put together with help from Mark Condy and Don Hampton, who are also rocket scientists at Poker Flat and members of the University of Alaska Fairbanks. Mark and Don are actually in Norway, launching rockets from Norway in the next couple of weeks as part of a combined European-American project to look at space weather over Norway. Kathy Rich, our range director at Poker Flat, is in the audience. I won't point the laser at you. And then Rodney Vierick is a graduate of UAF who has found his way to the Space Weather Prediction Center in Boulder, Colorado. And he gave me some material about how they view space weather. They're the part of NOAA, and they've become the government agency that advises industry and the government and everybody else who's interested about space weather and space. So the picture we have on the right is the launch that, just to highlight what we do at Poker Flat, is captured up by we launch rockets. That's what we do uniquely well. And this is for a time lapse. You can see the swirling of the stars. So the stars streaked out in the time that we took the measurements, the photograph. And then we have 4 rockets being launched in about half an hour. And part of what I want to share with you this evening is the unique capabilities of Poker Flat for doing that, and the unique science that Poker Flat can do because we have been launching rockets and know how to do it well. And so with that, I want to go back to what underlies most of our appreciation of space weather, which is the aurora. And this is actually a video from the night those rockets were launched, taken by Ron Murray from Clery Summit. So if you know that Poker Flat's 35 miles north of town out on the Steese Highway, one of the last pieces of driving excitement before you get to Poker Flat in the Chattanooga Valley is to go over Clery Summit and down the other side. And for those of anybody who's connected to the mine, the road is plowed beautifully to the top of Clery Summit because the mine workers getting out to the Fort Knox mine need that road to be in good shape. They work long shifts out there. And then oftentimes the road changes as you pass the mine, and you find yourself driving in a much more Alaskan excitement the last 10 miles to the range. But this is the view from Clery Summit, the pull out there at the ski land, and I want to play this. Let's see, this should work. It takes about 4 or 5 minutes, and there we go. So this is the results. There is music to go with this. Do you hear that music at all? Okay, I'm actually going to talk over the music, but I'll just let it play backwards. So this is, as we all know, living in Alaska, the aurora. And obviously it's a thing of beauty, and it's a thing that encourages us through our long winters with its beauty. But it is also the last piece in the whole puzzle of how the sun affects our Earth through space weather. We have this beautiful green light that comes from the glowing oxygen high in the sky at a distance of about 60 miles above our head. I always say the aurora is like a drive to Nenana. It's about that far away. And in this particular case, there's little hints of purple at the bottom. That's the aurora getting down to about 50 miles above our head. And what is, of course, wonderful about the aurora is that its structure. And that's not just a thing of beauty, it's also a huge part of the science of understanding space weather, because what we have is a world where space weather is happening at these very small scales. We have a process that starts in the sun, 95 million miles away, sends huge clouds in the solar wind of charged particles, and I'm going to turn this down. Hold on. Charged particles towards the Earth. And so here's the ignition of the rocket. I'm going to, leaving Poker Flat over the hill. That's the first stage ignition. And is this the tracer rocket at the start, or it's actually the launch? There we go. There's the second stage. It's the real rocket. It's not the decoy rocket. And what this rocket's going to do is we're going to see one last thing happen. This is the second stage of the rocket igniting. And then we're going to see a release in the sky in a couple of minutes, and this is in real time. No, that's the decoy rocket. This is the real rocket. I knew we had two rockets here. This is the first stage, and it ignites. And so what's happened at this point, while we're waiting to see the actual views, for this rocket to have happened in 2015, it means that in 2012, the National Aeronautic and Space Administration agreed to fund a rocket. It took 3 years of preparation with students and faculty at the university and also working with Wallops. So when that rocket was launched, and I happened to be the principal investigator for this rocket, it was one of the scariest things I've ever done, because in the moment that you decide to launch the rocket, you have made an estimate that this Aurora is what interests you. You've made a hope that everything in the rocket's going to go right. And next thing, Kathy is there at Poker Flat saying 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And you're like, I can't take this back. I can't in that moment tell Kathy, no, it was a horrible mistake, stop counting. It's not quite what we hoped. And we have students who are depending on their PhDs who've committed 4 years of their life to this point of the game. And so in this case, we were involved in an experiment to launch luminous trails in the Aurora to look at the winds in this region of the atmosphere, which we can't measure directly with satellites. We can't measure with weather balloons. Weather balloons are only getting to at most 20 miles high. This is at 60 or 70 miles high. And so as this trail deforms, we have cameras across the state, both at Poker Flat and up at Coldfoot and at Tulik Lake, all looking back towards these trails and triangulating them against the stars. And so by triangulating the position of all these features, in this case it looks like a little horse. It's not meant to, but it does, I suppose, if we take, that we actually can measure the winds, that we can reach out and measure the winds at the edge of space from the ground. The trails dissipate over time. This is actually the re-entry of the payload, because what's happened is you launch the rocket like so, and it just follows a parabola. What we're doing is we're recycling ballistic missiles that have got relatively elderly, and the military looks at us and says, well, we can deal with getting rid of these, or we can donate them to science. We're quite happy for them to donate them to science. And so they come to Poker Flat, and you can view this as sort of their retirement gig. They get one last trip to Alaska, get shot from Poker Flat, and there they go. And I just want to let this play a little bit more as it comes down, because you'll see something interesting here, and then I'll get into the talk proper. As I said, there's a whole complex set of processes that get us from the solar wind, when we think about the sun, that it's an unshielded nuclear bomb that gives us life. That's not maybe the best and coziest way to think about the sun, but that's what it is. And it's streaming out light and particles, and those particles come through a complex set of interactions with the Earth's magnetic field. And so you can see there's residual chemicals in the payload as it comes back in, and I'll just hold with this for a minute. And so today when I was talking with Ned Rosell about this talk, and I said, well, how many diagrams of the magnetosphere should I put in the talk? And he said, preferably none. You'll lose your audience. So they were all scrubbed at 4 o'clock this afternoon. So we're going to try and do this talk in terms of the visuals that we have in video and from various places associated with the rocket launching. So I'm going to kill that there. If anybody wants to watch the whole video at the end, we can do that. But let's get into the talk proper. So, slideshow. So the other thing I wanted to acknowledge while we're here, and this is going to be difficult to hear, I'm going to turn it up, this is the beep that you're hearing from Sputnik, which last October is the official 60th birthday of the space age. And the space age starts with the launch by the Soviet Union of the Sputnik satellite in October 1957. And it kicks off the space age. It's a small satellite. This is the Russian newspapers showing it rounding the Earth. It was a small ball. I think what makes Sputnik, one of the things that made Sputnik tremendously successful, was the fact that ham operators could hear that beeping sound. And in fact, that was intentional by the designers to create a radio beacon on Sputnik so that it would make it actually real to anybody around the world. And so this beeping sound, scientists from the University of Alaska, from the Geophysical Institute, were involved in some of the first official sightings of the satellite in North America. And so it's always useful to remind ourselves that the space age has only existed for 60 years. And based on that, we have Poker Flat Research Range, which actually is coming up on its 50th birthday next year, with its first launch in 1969. This is a picture of what you would see coming out to Poker in January, typically of any year. Our rockets are sitting on the ground. They are enshrouded in styrofoam. They have to be kept warm. They can be sitting, pointing in the direction they're going to be fired for 2 weeks before the launch. Because what happens is that NASA come up in December, put the rockets together, and then leave the rockets in place, and then you have a payload that you can't have freeze. So we pump in warm air with Herman Nelson's in at the bottom. We keep the payloads warm. These are also solid fuel rockets. There's a big core of solid fuel. If that gets cold and cracks, then the way that it burns will change, and it won't follow the trajectory we would like, and that would be a bit of a disaster. Remember, if you think about where Poker Flat is, 30 miles north of town, it's east of the pipeline. It's sort of wedged in between the pipeline and the Canadian border. Those are two of the many no-nos in launching. We're not here to take out the pipeline. We know that the citizens of Fairbanks would probably shut down the range 3 minutes later. The citizens of the state would. We also have communities to the north, all of the communities between us and the Arctic Ocean. And so we have to work out very carefully as the rockets pass over Alaska where they're going to go and where they're not going to go, and all the factors that go into that. The first releases at the range were barium clouds, clouds of metal that were launched, and they glow in the sunlight. So even though the picture shows that it's dark, they've risen high enough in the sky to be illuminated by the sun over the horizon, and they glow green. But what is of particular interest to scientists studying them is that some of them then become ionized in the sunlight, and they become charged barium. And that charged barium travels under the influence of the electric and magnetic field. This barium travels under the influence of the wind. And so in one experiment, you can separate out the effects of the electromagnetic effects of the Earth's magnetic field and the electric fields associated with space weather and the magnetic fields, and at the same time look at the winds of the atmosphere itself, and in comparing those two, understand the physical model of how all that works together. So, and I go back to the, okay, thank you. So, when we talk about space weather in general, space weather, this is the sort of the nerd description from this Space Weather Prediction Center, describes the variable conditions on the sun and in space environment that can impact the performance and reliability of space and ground-based technological systems, as well as endanger life or health. And it always, you know, the fact that endangering life and health comes after the technological systems we can argue about, but that's the definition. The definition that we have traditionally for space weather, the first is based on the idea that when we have space weather events, we have huge currents flowing in the upper atmosphere, and those currents create magnetic fields that we can measure on the ground. They actually they appear superimposed on the Earth's magnetic field. And so traditionally, since the 1930s, we've used an index, one number, to represent all of the space weather around the world. And that number is based on 13 observatories in North America, primarily Europe, Australia, New Zealand, and they come up with a number called KP based on the disturbance they see in the Earth's magnetic field on the ground. And the number goes from 0 to 9, and as the aurora becomes more active, and this is used as the general number if you go to any aurora viewing website. They say, well, what value of KP do I have a good chance of seeing the aurora? And, well, you always have a good chance of seeing the aurora in Utgarvik in Barrow. You have KP1 is pretty low. You always have a good chance of seeing the aurora in Fairbanks. And you go down the list to KP of 9, which is an extreme storm. And if they can see the aurora in Miami, something pretty radical has happened. But you go down the list through the cities as you essentially head south across the United States and Canada and back to the United States again. When we think about what people are worried about in space weather, the Space Weather Prediction Center will tell people that if KP is 6 and they are doing something that is sensitive to space weather, maybe they should consider not doing it. And the kind of things people talk about are, the main thing we have is the Global Positioning System. That is the first impact that we now see in our technology. The Department of Defense never foresaw how people would use the GPS when they actually put it in place. They certainly didn't see that it would become a vital part of you finding Starbucks when you're out of town. That was not in the Department of Defense's mind as a strategic asset for the nation. But if we think about all the places GPS has shown up, and for example, one of the examples, and I'll come back to this, is that people in the Gulf of Mexico who are doing deep sea oil drilling use GPS to guide the placement of their deep sea oil drilling, and they will actually put off their operations if they contact the Space Weather Prediction Center and they say we see a KP of 6. 2 days later, when the KP of 6 has come and gone, one number for the whole planet, and it didn't really matter. They ran their GPSs. They didn't do the drilling that they wanted to do, but they monitored their GPSs. They never lost GPS lock. Everything should have gone according to plan and would have gone according to plan if they call up the Space Weather Prediction Center and say, well, that was useless. They don't say it like that. But they obviously say it very politely, but they essentially say that was useless. So the question is, how do we get to something, what we're currently trying to do in space weather is get to the world between, okay, advising people to run out, particularly people who live in the marginal areas of seeing the aurora. Because we in Alaska don't really follow KP too much because there's always a good chance of seeing the aurora. And these precise technical applications. The other applications that you have are decisions being made in the electrical grid about when we have strong space weather events that we have currents in the electrical grids, the famous case of Hydro-Quebec back in 1989, where the whole system failed. But even without catastrophic failure, the electrical companies are interested in modulating how they load their transformers based on space weather events. Again, if it's a single number called, oh yeah, KP is equal to 6, we should do something, that's an incredibly blunt instrument and very quickly an expensive instrument for the time and money it takes to modulate electrical supply. So the 3 classes of events that we have, if this is the sun over here, and this is our model of the Earth, and this is our artist representation of the magnetic field of the Earth, around the Earth. So this is sort of our cartoon view of space weather. We have solar flares, and where we have radio blackouts. Solar flares are where we have intense brightening of the sun, and we have electromagnetic energy, light, and magnetic waves coming out of the sun. And as a result, we get ionization in the upper atmosphere, more electrons in the upper atmosphere, and we get HF communications. High-frequency communication or shortwave communication is disrupted. This is where the Geophysical Institute first starts at the University of Alaska, because in World War II, it was realized that in the fighting in the Aleutians, there was no communications when the aurora was active. And it's actually the Act of Congress is based that starts the Geophysical Institute to say we're willing to fund auroral research because of the strategic need for communications in Alaska. Solar energetic protons are, as part of this, when the sun explodes, it sends out a whole bunch of ionized hydrogen atoms that have lost their electron that are protons. This also, everything takes out HF communications, but these particles are strong enough to take out satellite electronics and cause failures in satellite systems, and we've seen that. But they've also become an issue in health. These are ionized particles that are energetic enough to lodge in the bodies of astronauts. And so and also in aviation, so that when we have major solar energetic proton events, those protons actually come into the Earth and come down into this region, this little gap here in the magnetic field lines over the poles. And at that point, we tell transcontinental polar flights flying from Asia to Europe over the pole not to fly, because they're going to be exposed, because they're high in the atmosphere, they're going to be exposed to potentially too much radiation, and those flights have to be rerouted. The airline companies don't need one number called KP to guide them in scheduling all their flights between LA and London. They would like something more. And finally, geomagnetic storms. Geomagnetic storms, these two will give you geomagnetic storms, but there's a whole bunch of other smaller effects that cause essentially for the magnetic field lines of the Earth to sort of wobble, shake, rattle, and roll as material comes out from the sun, as the magnetic fields come out from the sun, even if it's not as exciting as a solar flare or a solar energetic proton storm. And those will cause the aurora. So these will give us very good auroras. These will give us our day-to-day auroras. And in these, we have the electrical power grid is sensitive, HF communication, and navigation. And when I mean navigation, I mean the GPS. Because what's happening with GPS is we're using the radio waves from 3 satellites to triangulate our position if we know where the satellites are. For that to work, you have to know that the radio waves came in a straight line. What happens is, as in these storms, is that the upper atmosphere, the ionization changes, the path of the radio waves changes, the radio waves twinkle, just like stars twinkle as this happens. The radio waves get deflected slightly. And suddenly, it's not a big deal if you need to know where you are relative to 2 or 3 miles, but it is a big deal if you're guiding yourself down to tens of feet or 20 of feet. And that's increasingly what people are trying to do with navigation. So, in celebration of all the snow we've had, we've taken the snow plowing example from the Thompson Pass. As you know, the Thompson Pass is the record breaker of snowy places in Alaska, just outside Valdez. It is the perfect place for snow. We have the warm Gulf of Alaska. We have winds blowing off the Gulf of Alaska, rising up over the Chugach Mountains. They get cold, they drop all their moisture, and this is the result. And so Valdez gets to enjoy that beautifully in ways that we're only getting a sample of this year. This is the snowplow. Increasingly, snowplows are using precision GPS to be able to drive in whiteouts. And so if we have a snowplow, if we have Aurora, we lead to the potential that the snowplow is going to go off the road. It's not quite as funny, obviously, as it seems. But we also have, increasingly in agriculture, a world where people are planting crops precision to 5 centimeters, putting in individual seeds and watering and fertilizing, all that good stuff, in precision agriculture. We're also using GPS increasingly in surveying and road laying as just guidance for making sure that you've got a straight line. And as I mentioned earlier, in oil drilling. So all those are there. So let's talk about, all these people are very interested in the small scale, the regional effects of space weather. They're not interested. And so currently what we have is in the federal government and research agencies and with industries, particularly the airline industry, the electrical industry, increasingly the surveying industry. If you've seen the precision maps that have been done by people flying lasers from planes, where they make these very high precision maps, and they've led to both archaeological discoveries and natural resource discoveries by mapping in that way. But if you don't know where the plane is, those maps are useless. And obviously knowing what the plane is to several tens of feet is all about having quality GPS on the plane. So all the industries that you get that are now looking at space weather. The other last one I would mention is that ties us to, I suppose, one of the other talks that was given in climate change, is the question of what happens in the Arctic when we have increased traffic through the Northwest Passage, if we have increased in economic activity, what happens in search and rescue that depends on GPS positioning in the polar regions as we go forward. So rockets become a huge part of how do we reach out from Alaska, the last frontier, into space, the final frontier. And so these are examples of 2 types of rockets. There's about 20 you can choose from if you're a rocket scientist. You essentially show up with a brochure and NASA will walk you through. So it's the ultimate shopping experience, maybe. And so the rockets that we have come in several stages. There's a first stage that ignites, that gets the rocket off the ground, and that stage falls away and lands about 3 or 4 miles from Poker Flat in Caribou Creek. There'll be a second stage then that ignites, carrying the payload higher. And then there's the payload on the top, which is the science instrument. All rockets come with pointy noses, obviously, because they're trying to shoot through the sky, and we'll look at some of the speeds in a minute. When we talk about a payload, this payload, once it's free, maybe at a height of about 40 miles in the sky, has to open up. Well, this is barreling forward at about 1 mile a second. And you've probably got some interesting instruments, as we'll see, under that nose cone. You've got to eject that nose cone, which involves a small explosion, that you actually release it with an explosion. And you sort of push it to the side so that when you open your instruments from within, they're not going to collide with the nose cone. And that may sound comic to you. You would not believe the amount of time when you're a rocket investigator that you spend at Wallops working out all those scenarios, that you don't just go to all this effort and have a thud in space. So just to give you an idea, I don't want to go through all of this, but just to give you an idea of a small bit of the complexity of the rocket. This is a rocket that I was involved in 2015, as Bob said. And so this is what everything looks like on the rail, and then this is what it looks inside. And I just want to talk a little bit about, you've got a cone, or a nose cone on the front of the instrument. Here we had an instrument sitting just below the nose cone that you'll see in a minute opens up with arms when the rocket is free after we eject the nose cone. We have the electronics associated with the instrument that radio the results back to the ground. Then we have the actual, we're not interested in having rocket bits land across Alaska and just say there's rocket trash to the north of us. The people who run our national refuges are particularly prickly about the idea that we're going to turn national parks into rocket trash. So we need to be able to go out and collect the rockets. We also pieces when they fall to Earth. We also a lot of times are recycling the payload itself. We can recondition the payload and use it for other experiments. There's a parachute in the back so that when the rocket comes down, it does not come down as quickly as it left. So, and that's usually the way in which rockets are found on the ground. We have a bounty program for people living north of Fairbanks that if they come across rocket parts and tell us where they are, there's a cash reward. Did you want to say anything about that, Kathy, and advertise it at this time? And there is, the other thing is that like bullets, rockets are much more stable in their travel if they rotate, if they're spinning. So initially, the rocket can be spinning maybe 5-10 revolutions per second. By the time it gets to where it's making a measurement, we don't want the rocket spinning 10 times a second. In fact, there's a possibility that you'll actually rip, if you throw out booms, you will actually rip them off the rocket if it's spinning 10 times a second. And so we have de-spinning, which might be using weights on a string to de-spin the rocket to slow it down, that it's only spinning maybe at one revolution per second instead of 10 revolutions per second. And we also may have that if you send your rocket up and it goes up and it comes down, it doesn't automatically turn. So if you wanted to turn and make 2 measurements for the price of 1, you want to make a measurement on the way up and the way down, then you've got to have some kind of navigation in there that puffs gas out of the rocket and turns it around, a small little jet engine. And so all of that comes together to make a payload work. So I'm going to do this, and then I'm going to break out to another video. Just to give anybody who wants sort of numbers, I realize graphs aren't the most user-friendly thing. It's 7:30 on a Wednesday night. But to give you an idea of the kind of speed, so this is the rocket path. We get up to a height of about 100 miles in 200 seconds after we launch. In our case, our experiment that we were interested in doing was between 40 miles high and about 70 miles high. So we had to have everything working 60 seconds after turn on. So we have a rocket sitting on the ground, and rockets are fast and stressful. The whole rocket flight can last less than 10 minutes by the time it comes up and comes down again. The payload experiences G-forces. You start from at rest, and within a few seconds, you're traveling at 15 miles per minute. And just to put that in reference, 60 miles an hour is 1 mile per minute. So you're going at 900 miles an hour. And that's the ignition, and then you slow down. And the reason you slow down is because your first stage of the first stage of the rocket is burnt out. You drift, if moving at 900 miles an hour can be called drifting. And then your second stage ignites, and you speed up again really quickly. And you get up to 3,600 miles an hour. And then that burns out, and then you drift through your experiment. And we don't want to be ignited and firing as we get through our experiment region. We want to get fast enough, somewhere about here, that we can drift through our experiment, go through our parabola, and come down on the other side. And so that's what we're doing. And I just want to show you then the ignition of a rocket from Poker Flat, what that looks like on the ground in slow motion. Presentation and high-speed video. So hopefully this will work. So this will be black for a minute, but there you go. It ignites. And this is all very much in slow motion. And you'll notice that the rocket comes flying out of the styrofoam. The styrofoam is all left behind, and away we go. And I'll show some other rocket launch pictures. But this is what happens in real time. And the forces at this point, given the accelerations, can be 5 to 10 times the acceleration due to gravity. So there's a huge amount of testing that goes into that to make sure that your payload just doesn't sludge at the start, or all the mechanical bits fall apart in the payload as it takes off. So that's what rockets get us. As I say, the payload I showed you just a minute ago, this is with its arms extended. There it is with its arms in the vertical. This is me and colleagues from Emory-Riddle, Colin Triplett, who was a student here at the University of Alaska, doing the publicity picture for NASA about how happy we are to be at Wallops working with our rocket. So there's the launch video that I just showed you. I did embed it, but I'm going to. So I want to talk then about the experiments, that sort of the current generation of experiments at Poker Flat. And this is an experiment called HEX. It's very important in rocket science to find what people think is a cool name. The real name for the experiment was the Horizontal E-Region Experiment. The E-Region is the region of the atmosphere at about 60 miles above our head. Don't worry about it. But HEX became the short. Everybody is EX because they take the EX from experiment, or they might take the E from E-Region, depending on who you talk to. And this is a rocket that was launched out of Poker Flat to say, okay, when we look at that aurora that you all saw at the start, that aurora is part of a process that's heating the atmosphere. It's actually boiling the atmosphere at a height of 100 miles, because that light represents a whole bunch of particles that are coming in, and they create the light when they collide with the atmosphere. But there's also a whole set of currents and associated with those moving charged particles that are streaming down the magnetic field lines to that point. And they're essentially boiling the atmosphere 80 to 100 miles above our head. That boiling propagates all the way up through the atmosphere. And it actually impacts the drag on satellites 250, 300, 400, 500 miles above our head. That's the interest of the long-term satellite community about how we impact the satellite orbits. That boiling also causes all set of chemical changes in the atmosphere that give us the space weather effects associated with geomagnetic storms, the twinkling in the GPS, the changes in the electron densities that cause the radio effects. So what Mark came to is, okay, if that's the theory, let's launch a rocket into an auroral arc. This is the view from looking over Alaska, the satellite view, and actually see what do we expect if there's boiling. Well, what do you know happens in your an electric kettle or on a stove, that at the hot point there should be rising air. So he wanted to fly a rocket, take it up to about, fire the second stage so that it would be about 30 miles above our head. Sorry, so it would be about 70 miles above our head, and then turn it sideways. And it took him about a year to get NASA to agree to this. When we think about a parabolic trajectory, just a simple trajectory which we do in basic physics of saying you push something or you throw something, it goes up, it follows a parabola, and it falls. Our rockets aren't guided. We don't want them to be guided. We want them to just follow that simple parabola based on the way that they're launched, so we know exactly where they're going to go. If you have a guidance system on board that can actually steer the rocket and fire the motors at height, there's more chances of something to go wrong. And NASA are very frightened by this, particularly because we're launching our rockets over communities where people live. And so to get a rocket to fly horizontally took a long time with NASA to decide how you deal with that. It is not a solution to say you will explode the rocket. If something's going wrong and you're on the ground, say, let's explode the rocket, because then the rocket disintegrates into millions of pieces and they all come raining down. And that's not a good plan. That's completely uncontrolled. So that's not the option. The Chinese government several years ago exploded a satellite in space, and people were really annoyed because they said, now you've littered the space lanes with debris, which we have no idea what the consequences will be. So what he decided to do was release little puffs of air, I'll just show the video, and see what happens in the winds around the auroral arc. And so he did that. And I'm going to show the video first. I'm just going to jump back out to the video, and I'll come back into this. And the video is, so this is what he did. So this is, first of all, his whole rocket plan. So this is, let me just pause this as we turn it. So he's got a computer animation. This is Poker Flat. This is his main rocket. It turns sideways. It travels over Alaska. This is his picture of an auroral arc, if we think of an auroral arc as a curtain down the middle. And these are his measurements of wind, which I'll show you how they worked in a minute. And then he had a second rocket because there was a nerd question about, okay, you've measured what's in the horizontal along here. How do you know how the winds were changing with height, due to the height of the aurora. He overflew Arctic Village. He had cameras in Old Crow, and he had cameras out to the west, and it'll come up in a minute. Toolik Lake, right there. And so this is the design of his experiment that actually worked. He flies through the auroral arc. He measures all these winds, and we see these streams of wind sort of around the aurora, but we'll see some surprises here in a minute. So that's what his design of his experiment was in a sort of a computer graphic kind of way. So then if we were sitting at Toolik Lake, or we're sitting at Arctic Village, which was overpassed by the aurora, then this is what we see. So what you're seeing is this is just a grainy picture of the stars in the sky with a very sensitive camera. And what you're going to see is the rocket appear from the left and cross the scene. And the rocket lets out these little puffs. And so now the puffs are going to drift upward to the west, actually. And so what we are doing is we're measuring the wind by having 3 cameras on the ground looking at where these puffs are, using star maps to actually give their location, and then track them in time as they drift across the sky. And this is, as I say, there's no other way to do this. This is how we reach from the ground into the edge of space in these experiments. And so, if I haven't lost my PowerPoint, so what did he find? So there's the picture of the little puffs. So all I want to point out in this, and this is where Ned said you're getting dangerously nerdy, because this is actually a picture from a fun reading journal called the Journal of Geophysical Research that publishes about 25,000 pages a year of high-core, black and white, dense text describing our world and how it works. And so I don't want to give you the whole slide. The big thing he found, that when you come and talk to Mark about the paper and don't wade through the 20 pages of dense text, is that he did not find that there were boiling upward winds around the arc. So just in terms of the diagram, this is latitude along the magnetic coordinates. Remember, the magnetic pole is over Canada, slightly west of the North Pole. And so this is just distance, if you want, north of Poker Flat. The green area marks where the auroral arc that we saw was. And what he found is that none of these numbers cross 0. All these winds are negative or downward. I'm not going to talk so much about the other stuff at all. That's all technical details for space physics people, which I'm happy to share at the end. But that was the big thing, was to say, okay, we have this idea of how it should work in the large. How do we come with rockets to say, okay, well, let's question those assumptions, particularly if the stakes are continuing to rise with what we do with our science? And so we call this, generally this challenge, as looking for the devil in the aurora, because the devil is in the details. For our models to work well, the physics is happening at those small scales and plays out to those larger scales. You can't just come in at the large scale and say, I'm going to come up with a solution of what happens. And so what has happened in the current generation of rocket launches at Poker Flat, people say, okay, it's very nice to have a measurement exquisitely along the rocket trail, but how do I know what's happening around it? How do I know that that's actually representative of what's happening in the arc? Mark came to that by releasing a trail of luminous gas and looking at how it moves. Increasingly, people are saying, let's actually take the complexity of a payload and let's add more by actually having small payloads pop off the payload. So now we have, not only do we have the payload holding together with its primary instruments, but we've got little loose parts that we're going to eject, and hopefully they're going to spring out, some of them literally with springs, 60 miles high in the sky, and make measurements. And here are examples of just 3 missions I just want to share with you. So the first one is what is affectionately called by Christina Lynch at the University of New Hampshire, the hockey puck experiment. These are 5-inch wide hockey pucks. Now, they're very clever hockey pucks because they have magnetometers in them. They can actually measure magnetic fields, and in measuring magnetic fields, they tell us something about moving currents, because, you know, all moving currents create magnetic fields. And so in her payload, she has a nose cone. She has a boom that's going to swing out when the nose cone is ejected. But she also has 4 hockey pucks that are going to fly out, and remember, this is all twirling at 1 or 2 times a second, rotating, and she's going to release these hockey pucks, and they're going to go flying out, and then, but remember, when we let them fly out, she's not sending them out explosively, she's sort of giving them a nudge on a spring. Now, Not quite as much effort as it takes to push a teenager out of the house, but maybe a little bit more. But they come out, but they then travel with the rocket. And so this was her experiment launched from Poker Flat. 100 seconds after it launched and survived all its G-forces, she had 4 little satellites traveling along with her primary payload. She traveled through the auroral arc and then over Kaktovik. These have moved further apart. They're now 1.7 kilometers versus just a couple close by. And they spread out a little bit more, but she now has a constellation of measurements through all the complexity of the auroral arc. And I just want to show you how that worked. So she continued that. That was a launch entropy. She's continued those technologies with that success to measure also not just the magnetic fields, but also to measure the charged particles, particularly oxygen, which is dominant at the height of auroral maps. This gives you this is the rocket she would have used. There's your standard human at about 6 feet. There's the first stage, the second stage, and then this is her payload. The payloads are all assembled at Wallops Island, Virginia. The way this works is NASA provide this, and NASA then give money to a university to build the payload instruments. So most of the instrument people are university professors working with students. Then you bring all the parts to NASA. This gives you an idea of the complexity of the payload as it's all wired together. This is Christina looking into how she's going to eject these small, this set of ejectable things out into the aurora. This is an example of how this happens. And so at Wallops, we have a test facility where these are NASA-approved mattresses on the ground. And all of this is being so what happens when you go to Wallops Island, the whole payload is assembled, and essentially I can't use that word, but they beat the ... out of the payload to say, how do we know that this is going to survive launch, that it's not all going to fall apart? How do we know that every mechanical mechanism on there is going to work according to plan? Hold on, don't do that. Okay, hold on, sorry. And so, yes, down to we have a big bay where things are exploded, things are twirled, things are vibrated, things are shaken, and every step of the way you have all the control signals coming back from the payload to say, did it still work? Did it still work? Were there any glitches? The parts land, as I say, on the NASA-approved mattresses and are picked up and put back in. Another example of this, so another example of this is the ASP experiment launched a couple of years ago, again, where we have a rocket with all its primary measurements, and we're throwing out measuring electric and magnetic fields. The way that you measure electric fields is to look at electrical differences along long wires. These are literally wires that spin out with little weights at the end, that's sensor weights at the end. There's GPS on board to communicate back to this, to communicate back to the ground. This is what they look like sitting at the ground at Poker Flat when they were being assembled at Poker Flat. And again, they too have to be tested. And here the arm comes up. And on a sunny day in Wallops Island, Virginia, everything appears to work. So hey, we're packing it, we're sending it to Alaska. Everything works according to plan. In this particular case, everything worked according to plan a year late. They did a bunch of testing in 2014, didn't quite work. The communications weren't working. They stayed at Wallops for another year, got it all working, and the launch happened in Poker Flat a year later. Again, I like this one, which is caution, Pyro's installed, so that when they're assembling the rocket at Poker Flat, they're reminding everybody that as the rocket sits in payload assembly, there is live explosive parts in the payload, and being careful. But this payload had booms, this payload had the parts that were going to be ejected. They were all tested at Wallops and spun. So you have all the hardware at Wallops for absolutely testing everything before it becomes in the box to go to Poker Flat. Finishing up, I would just say, Rocketry is an example of where it's not all about math. And I don't mean this, I do a lot of math in my job. But it's not always about math, and math isn't, just because you got the math down isn't your guarantee of success in science and technology. The other thing I would say is Poker Flat at age 50 is the only university-operated rocket range in the world. Yes, it's with a huge partnership with Poker Flat. We have a staff at Poker Flat all the time. But when it comes time to launch, you'll see at the end the staff becomes much larger. But a huge part of that is the opportunity for students in Alaska, and that students come to Alaska and come and live in Fairbanks. And I've known many students who talk about coming and living in Fairbanks and saying, I am really ready to graduate, I can't take another winter from places warmer than Fairbanks. But this is an example of two students, Jintai Lee and Jennifer Alspach, who worked on a telescope for the Super Soaker launch this spring, where we were shooting laser beams into the sky. We did a water release, and we were targeting the water release with lasers to see if a cloud would form from the water release. The light from that laser came back to this telescope, and then we were able to analyze what the cloud was doing. The range also is successful. Why is Poker Flat successful over 50 years? Also because it's become a cluster for a whole host of experiments. The laser experiments aren't just paid for by NASA. They've received support over the years from the National Science Foundation. So there's a whole bunch of partnerships at the range that keep it going, that allow opportunities for students here at the University of Alaska. The other thing that Alaska does very well, that we're very lucky with, is we're sitting in the center of the state. We can therefore instrument the whole state around us. I'm not going to go through the whole list of instruments here, but these little dots are GPS receivers. You can use the fading and the twinkling and the GPS if you're not worried. If you know your position, then you can look at the twinkling and work out what the atmosphere is doing. If you don't know your position, you can't work out anything. So if you fix the GPS on the ground and survey that site, then you can use it as a remote sensing tool for the atmosphere. Anyway, Poker Flat sits in the center of this with rocket launching capabilities, with big radars for looking at the atmosphere, supported by the National Science Foundation, and HARP down the road. If any of you are interested in a grand day out in August, I think we do a bus tour every year. Is that right, Bob? We'll be doing it this year. Anybody who wants to spend a beautiful day out driving to Gakona and back and seeing a really exquisite radar antenna and other science stuff, we advertise that. We have antennas out through the Aleutians. And so this whole region becomes a giant laboratory for studying space weather that no other place in the world has. One of the things that's happening in Norway this week is there's an experiment to do a payload that's going to eject loads of pieces into its measurement. That was originally slated for Poker Flat until Kathy was doing the safety analysis and said, you know, the idea that there's going to be 16 pieces of metal floating through the sky across Fort Yukon, Toolik Lake, Arctic Village, Kaktovik, maybe we should look at this again. So NASA looked at it again and said, you're right, we're going to take it to Norway. And the reason they're taking it to Norway is because in Norway they launch from the coast and it goes out over the ocean. It goes out over the Arctic Ocean. And so there aren't a lot of communities for all the pieces. So that payload is actually proving itself there, and hopefully can come back to Poker Flat in some future experiments. The last thing I'd say is this is the picture of the morning after. So this in 2015, this is the whole crew. I think, Kathy, that's you. So it's the crew both of, these are all the people who've come from NASA, up to 60 people. We have some University of Utah people there. I think I'm in there somewhere as a University of Alaska person. But this is, and what they talk about is the fact that generally we're launching under clear skies. The big thing in taking this picture was that it was 45 below. The conversation among the people from Wallops Island, Virginia, was, of course, that they had launched the rocket at 45 below the night before, and that was exciting to them, just that. But that's the partnership we have to continue doing the unique kind of science that we can at Poker Flat. Thank you very much.